Well, hello and welcome YouTube to Mr. Robinson's Q&A Power Hour for Integrated Math 2. Now, I just did a Math 1 video, so you can, if you're in Integrated Math 1, you can find that part on YouTube, and then Integrated Math 2 is then coming up subsequently after. If you want to find a specific question that was asked by one of my students, to which I will answer here, go ahead to the description section down below, and you will find it in the description section down below, and find a corresponding timestamp to that very specific question for which I answered, or at least tried to answer, for my students here. So yeah, what this whole thing is about is every 2 weeks, students submit questions to me, to which I answer for them. They should be relevant to the content in the past couple weeks of material. And in these past couple weeks, we've been working on exponential properties, graphing exponential functions with growth and decay, positive or negative, modeling exponential functions with growth and decay with like money or population, and solving quadratic equations and solving quadratic equations with complex solutions possibly, and working with complex numbers as a whole, as well as rationalizing denominators, simplifying radicals. Gosh, we've hit a wide gamut here, so I sure hope, well, I hope they understood it, and for those who didn't understand something, they asked a question, so I hope that I can help them understand it after this. So let's go ahead and take a look at the question lot here, and let's get it started. The first question asked is, what happens when A is negative? So they're referring, I assume they're referring to y equals ab to the x power. When we've been graphing exponential functions, guys, we've really been focused just on the most generic form of this. No vertical or horizontal translations. Y equals ab to the x power. Now, I hope you can find this, to the student who asked, I hope you can also find it in your notes, and I hope that I provided it for you. If not, I'm a bad teacher. Let's assume that b is greater than 1. Let's assume it's an exponential growth problem, just so I can make mention here. I mean, I could go further, depends on if someone asks here, but when a is, well, actually, let's not assume b is necessarily greater than 1, but when a is greater than 0, you're going to see one of two things happen here. Well, it's going to be a positive function, which means if there's an asymptote on the x-axis here, your graph will be above it. Now, here's an exponential growth problem when a is greater than 0. And here would be an exponential decay problem when a is greater than 0. It's still above the asymptote here, which is on the x-axis. So it is a positive graph there. That's when a is greater than 0. Okay. Now I don't have much room, so I'm going to go ahead and, well, I won't erase it. I'll just kind of flip this over. When a is less than 0 and we have exponential growth, it's going to look like this. That was perfect. It's going to end up looking like this when a is, probably got to change that less than sign, huh? The greater than to less than. When a is a negative number, we'll have a negative graph there. And negative doesn't necessarily, well, here it does, but because there's no vertical translation. But, you know, this could be a negative graph and be shifted up here. You know, we're not doing shifts, but it has some positive points. But the point is it's below the asymptote, and it kind of increases down that way. So when a is less than 0, it's going to be exponential growth, negative exponential growth like this, or negative exponential decay like this right here. And of course, some people have trouble with negative exponential decay, wondering why is it going up. I don't know if someone asks about decay again, they can, but I've answered a decay question in the last video, because I guess we were already working on this graphing at the time when people were asking about it. So that's what happens when a is negative. I know that was your question. When a is negative, we are going to be getting graphs below the asymptote. They're still exponential in nature, and that's what occurs. Okay, so that's the end of that question. Next question is, what exactly does growth and decay mean? Growth is the form of increasing your rate of change of something over time, your amount of something, but it's increasing more and more as time goes on. So when we're referring to some sort of growth, if something takes off more and more in this direction, it's experiencing growth. It's not just growing, but it's experiencing, let's see, how do I say it? If I have a linear function that's going like this, there's no growth. It's all about rate of change. This, if this was linear, if this was a straight line, it's a constant rate. If I make $6 per hour, my rate, my salary, my dollar rate has not changed. It is constant. If I make $6 1 hour, and then $12 the next hour, and $24 the next hour, and it doubles each time, there's a growth there. If I'm driving 50 miles an hour, even though I'm changing my position over time, I'm going further and further away from where I started, I'm driving at a constant rate. If I step on the gas pedal and I start speeding up over time, that's that form of growth. Now, you can have negative growth as well, growing in the negative direction. Negative doesn't necessarily mean bad. It just means the direction opposite of positive. It could mean bad, all depending. But negative growth, that way, if something grows negatively, it takes off in that way, in the same vein, like losing money, like my stocks. Decay is when you're losing something and it's approaching your limit, which in our cases is an asymptote, when it's getting closer and closer to it from the top or from the bottom. You might have heard of decay when it comes to like radioactive decay, where every compound of something, whether it's, gosh, I can't even think of anything, of carbon 12 or carbon 14 or whatever. Radioactive decay is when you're losing material over time, but the thing is that it doesn't lose it in a linear sense. If you lose 50% of something every hour, you lost 50% of this and it becomes, where's my hand? 50% of this and it becomes that, 50% of this and it becomes that. You get halfway closer and closer to something, and your distance from one spot to the other decreases less over time because it starts to taper off a little bit. It's kind of like when you like drop a tennis ball and it bounces up in the air. Let's say we had a tennis ball that bounced up half the previous height each time. You drop it from 8 feet in the air, and it bounces back up 4 feet. Now when it goes down again, do you lose another 4 feet after that? Does it just bounce up 4 feet and then it just hits the ground? That's it? No, it would then have a rebound ratio still of a half, and it would bounce up to 2 feet, and then to 1 foot, and then to half a foot, and then that point, and then eventually I guess it comes to rest because physically it something happens and it resists. But even though when we calculate it, it says no, it stays above 0. It never actually truly goes to rest. But no, it goes half its previous height, and it has that decay. That's not radioactive decay, but it has that concept of just getting half the height each time and approaching that 0 in that sort of way as a limit. I don't know if I answered it well enough there, but the reason I'm dodging that a little bit is because I answered exponential growth and decay in the last thing, but that was more as far as what it looks like on a graph. So now I'm giving you kind of the concepts and models of what it really is, like what it is as words. So I hope that helps. Okay, what are some similarity and differences between exponential growth and exponential decay? Well, okay, so see, I kind of did answer this in the last video. They're more so about differences than similarities, but the concept here that I guess I can point to from a previous question I already answered here about, okay, well, this is an example of negative growth and negative decay. What are similarities and differences? They both have factors to them. I can double one way and have the other. Here's something that's similar. If I have some sort of, let me get rid of this. If I had some sort of example like y equals 4 times 2 to the x versus y equals 4 times 1/2 to the x, notice that 2 and 1/2 are reciprocals of each other, which means they'll be experiencing exactly opposite effects here. 4 times 2 to the x power starts at 4 right here, and then it doubles each time x increases by 1. And if I go to the left, that must mean it's taking half of what it had before as x decreases by 1, and it does that. Whereas the other one, 4 times 1/2 to the x, it goes half its previous amount when x increases by 1, and then it doubles as x decreases by 1 there. So you're getting an exact mirrored opposite effect whenever you have a reciprocal form of growth versus decay. And that's not super important as far as answering your question, but it is important for students who are having troubles with the fractions. Even if for growth, people are understanding how to double going one direction, but you might have trouble going the other direction. And just understand that if I'm multiplying by 2 one way, I am dividing by 2 the other way. Right? That just seems to make sense. Those are inverses of each other in that form. Or dividing by 2 is also multiplying by 1/2, if that helps. And that might help, because when I say multiplying by 1/2 going this way, that does mean dividing by 2. And if I'm dividing by 2 this way, then I am multiplying by 2 going that way. Anyway, I don't really know what much more to say about that. You're not talking about positive versus negative here, and this isn't really a good answer to your question outside of this, but did you know that positive exponential growth and negative exponential decay both go up? I don't know if that's something that you wanted to hear. And did you know that conversely, positive exponential decay and negative exponential growth both go down? I don't know. Anything else I answered in the 2 weeks ago's video on growth and decay there. So I hope that I covered some other new bits that might have been very interesting to you or might have helped answer the question that you asked. Okay, next question is, when doing the graphing for exponential functions, how do you know if it's negative or not? It's very simple. If your a is positive versus negative. If a is positive, then it's positive exponential growth. If a is negative, it's negative exponential growth. Or decay. It's a negative exponential function or whatever. One thing I haven't been doing with us, and we should have been practicing it more. I don't know why I haven't. We've done it just a couple times, honestly. I really should be looking at this more. But what you asked made me think of something. Sometimes you don't see the a value. So what if we had y equals negative 2 to the x power? Hopefully we've understood, guys, that b either can be between 0 and 1 or greater than 1. B cannot be a negative number. What we're looking at right now is not a negative b. This is equivalent to saying, guys, y equals negative 1 times 2 to the x power. See, b is 2. B is 2, and a is negative 1 here. And I hope that you recognize that here. I hope that you recognize that b is 2 and a is negative 1. Anyway, because a is negative, even if you couldn't tell here, that's the a. Because a is negative, we'd have a negative function, which, as I answered in the very first question on this, if you want to know, it's when you're below the asymptote. A is negative, you're below the asymptote. A is positive, you're above the asymptote. And because we're not doing any translations and such, you don't need to worry about that right now. You can worry about that next year when you're taking integrated math 3. All right, next question. Can a problem with two radicals, both negative numbers on the inside, be left with the solution of more than one radical as an answer if there is no perfect square in the solution? I would... Can it be left with it if we're simplifying correctly and if the radicals are the same, have the same root, if they're both square roots, if they're both cube roots, whatever. Like, we've been dealing with square roots when you're talking about this for the most part. So if they're both square roots, both being negative doesn't have to do with the answer here. If you're simplifying the answers, we should only have one radical. So I don't know what your both negative numbers on the inside has anything to do with this. It doesn't change the answer to your question. So I'm going to ignore the both negative numbers on the inside part. Whether or not you have negative numbers isn't going to change what I'm going to say. But if you have two radicals, let's say they're both square roots. I like that you said radicals, but because we're dealing with square roots here, let's say that. If they're both square roots that you're multiplying, and I'll show an example of what this person's asking. So if I have something like, and you said there are no perfect squares in the solution. So let's say we had something like the square root of 2 times the square root of 7. I'm making it simple. And we're, don't leave it like this. Ultimately, make sure you join them into one. Call it the square root of 14. There is no square root on the inside. There's nothing else to factor. Turn it into this. Don't leave it as two different square roots. If they're both negative, that becomes negative square root of 14 for a reason that you might not be thinking of. It's because that's I root 2. I root 2 times I root 7. Sorry, which is I squared root 14, which becomes negative root 14. Not because the negative, yeah. But anyway, them having negatives inside is not going to change that. Now, if they are radicals of different roots, if this actually truly was the square root of 2, come on. If this square root of 2, well, actually, I'm not sure if this is right. Let me think about this. If this is the square root of 2 times the cube root of 7, you could leave it like this. You know what I would... Yeah, you would leave it. Yeah, you would leave it like this. We often don't deal in those terms. What I was going to say is you could convert them into fractional exponents, but if these are different bases, it's not going to matter. You would just leave it like this otherwise. But yeah, if they're the same, if they're both square roots or both cube roots or whatever, multiply them both. If there's something to simplify on the inside, again, you go ahead and do that, but write it down as one radical. That's the most simplified form of what you have. Again, the negatives inside there is not going to change the answer to your question. Okay, here we go. Next question. I understand what you mean when you talk about imaginary numbers. Good. However, how are they used in real life? Also, we only learned about the I squared equals negative 1. Are there more equations similar to this, and will we encounter them in the future? Excuse me. First of all, when you submit the questions, I'd rather that these were separate questions, because now I got to make sure I don't skip one part. I'm going to try and answer your second question first. I squared is -1. Remember that I is not a variable. It's not a constant either. It's a modifier. It's a way of telling you you're dealing with imaginaries. So I squared equals -1 is very unique in that way because it had to do with a rule for explaining numbers. But there are other constants that you'll see, and I don't know all of them, but one off the top of my head I can think of is pi. Pi is a constant that represents 3.14, and you might say no, or 159.26535. I'm not going I don't know very many. ... It's irrational, but it's a constant. And you might be saying, no, Mr. Robinson, I'm talking about letters. Well, this is a letter. It's a Greek letter. Pi is a Greek letter. It's a symbol to most people like us. But there's also this letter E. E is called the natural constant. It represents 2.718. I don't know, something. I can't remember what else. I wish we got to go into this literally in the thing we're talking about right now. When you guys go into IM3, you're going to be learning something called continuously compounded interest, and you are going to be using the letter E for things. You're going to be using something called natural log, which has to do something with the letter E. So you're going to be using this number here. Now, you often will just let the calculator do it for you, or your answer will just have an E in it. So us changing I to -1 is something that we get to do on our own. Otherwise, with pi, we either leave the answer in terms of pi or you let the calculator do this part here. So I being very specific as its own constant like that, or squaring it, I should say, is probably a more unique version. Okay. Now to your other question. Your other question asks, how are they used in real life? Okay. The one thing that we're not doing here in IM2 is really looking at I on its axis. And when we draw a number line, a number line's one-dimensional. We have 0 here, we have 1, 2, 3, and -1, -2, -3. It's one-dimensional. It only goes left and right. Our real number line, this is called the real axis. Our real number line hits every number that we've ever kind of seen in the book. It hits a billion, and it hits pi, and it hits E, and it hits -10. It hits every number that we've played with before. But in something like, especially in physics, there are other dimensions for which we want to account for something. And listen, imaginary numbers aren't the only way to do it. It's not the only way to do it. But the imaginary axis goes off of the real axis, and it has another direction. It adds dimensionality to it. If real numbers are like an x-axis, the imaginary numbers go on what's like the y-axis. So here's your imaginary axis here. There's real and there's imaginary. So boom, imaginary. So this would be 1i, and this would be 2i, etc., and -1i and -2i like that. And you're on that axis. So when we look at a complex number such as -3 plus I, that's right here, -3 plus I. Now, how is this used in real life? Well, the same way how numbers at certain points, just like x and y, how some number labeling something can be attributed to something else when it comes to its own scalar bit. This is not a physics example, but this is just me saying that, what if the x was about time, 1 o'clock, 2 o'clock, 3 o'clock, and at those certain times we could do something like measure temperature. Right? At 3 o'clock, temperature's here. Whatever, like that, right? But in physics, this is used a lot in what are called phasors. It's used in circuitry. It's used to represent oscillation. When you guys take pre-calculus, you're going to be learning more about, well, we might be doing it here, but not for periodic functions. You're going to be learning about like sine and cosine periodic functions, doing something like this. This is used everywhere in physics, especially in circuitry, in things like sound waves. You guys might know something about sound waves going up and down, stuff like that. This is really important in circuitry, because what we can do with the eyes and such, by the way, I think I already said this, there's more than one way you don't have to use imaginary numbers to do what we're talking about. This can be completely used with x and y, but then you got to use trig functions like sine and cosine and things like that. But when we use imaginary numbers to describe -3 plus I and -2 plus whatever that we have here, this can help calculate things such as when you have what are called alternating currents. And in an alternating current pattern, you have one current going this way and another current going this way. And to make sure that they are running in tandem with each other to cancel each other out, this can help avoid, causing, being electrocuted or something. Because what you can do is cancel out, say that this is at 2i, whatever, and this is at negative 2i at that same real number. 2i minus 2i is 0i, and they cancel each other out to, they phase each other out. They're, what's the word? I don't take physics, so I'm not, this is hard for me to talk about. You can look this stuff up online. They're, what's the word? Their resultant phase cancels each other out, and what you have is something flat, so you aren't getting any sort of electrocutable kind of current involved in something. That's what alternating current kind of does and allows. And anyway, the point is you can now calculate it, that at any part of your phase here, which is measured just on the real number axis, the imaginary numbers are used to do that. Now, imaginary numbers are also, and they're used more so in math, and when you say real life, physics, it's used a lot, but in math, it's used in what's called the fundamental theorem of algebra. It helps explain the idea that any polynomial of any degree, like an x cubed, will have 3 complex solutions to them. It might have 2 imaginary and 1 real. It might have 3 real and no imaginary. It might have 1 real with a multiplicity of 3. We're not talking about those at all. And no imaginary. But the point is the imaginary roots help explain the idea that something of degree 3 has 3 complex roots. And the imaginaries help explain that. And they do show when we plug those things in, we can get the number back out that we want. And I know that I've shown that in some of my classes, in my IM2 classes, but by actually plugging in my solution back in and seeing that that explains getting the answer, starting with the idea that I squared is -1. The other concept to this, of course, is that, numbers, that math and numbers and stuff, that is a creation of us, of humans. Physics and chemistry and such are not creations, they're discoveries, and math can help explain what they are because we made our own math rules. But math has a set of rules that we decided, and I mean the decisions upon them make sense, including a negative times a negative is a positive. But the idea of that is whether you square a negative or positive number, you get a positive result. And so then when we take the square root of a positive, we only get a positive, back out. But, what about taking the square root of a negative? Why is there not a rule defined for that, and how does that kind of work? Well, we have this number system that kind of helps explain it to help with what's called, once again, the fundamental theorem of algebra. You can look this up on YouTube, what that means. I don't know if you'll make sense of it, but the concept is it helps define our number rules in a way that kind of it realizes everything into form. And I say that with no pun intended. I don't mean like real numbers, but it realizes that our number rules do have exceptions to things that our system does, and we need a definition for it to kind of make sense of it. And that's different from something like dividing by 0. Dividing by 0, zero holds a different speciality in its own regard, and I hope that you understand that 0 amounts of something. I don't know. I'm not going to get into that. You can ask Siri about dividing by 0. She gives some intricate answers. But anyway, I hope I answered both of your questions there in kind of a big way. And again, you probably don't know much about sine waves and oscillating patterns and stuff with circuitry and resistors and periodic functions and all that. But when you get into that stuff, I think the answers to the other parts will make sense. Again, I'm not a physicist, so I don't use imaginary numbers in my line of work other than teaching it to you guys. But I don't use it in actually like the field. But if there's one thing I can state about it is that it helps give a new direction to our number system. Real numbers just go left and right. Imaginary numbers gives the two-dimensionality to it. Now we can look at things up and down off of that pattern, and we can use them for that same way. Okay, why do we call them imaginary number when they are really not imaginary, but they are not real numbers? So that's a good question, because you hear me all the time. I have to preface something by stating imaginary doesn't mean they're made up. Well, technically, listen, all numbers are made up. That's what I just stated in the last question here. The number system is created by man, by human, I should say. No, it was probably by man. It was probably an Archimedes thing. Anyway, or the Greeks and Romans. And anyway, why do they call them imaginary numbers? Well, first of all, I'd say if they had a better word for it, I guess we'd be calling it that. But maybe, see, don't think of imaginary as made up. Think of imaginary as something that we cannot perceive on a real number system. When we graph something on the XY plane, that is a real XY plane. We're not going to be able to see and determine what those imaginary numbers look like. And I should Google this. I haven't done it before, but when we have two complex solutions to a quadratic equation, the idea is that the the quadratic, the parabola, never crosses the x-axis. So what does it look like when you have these two solutions? What does it look like to cross? And I'm sure there's a whole nother imaginary plane that we don't see that goes in the third dimension, because we're in 2 dimensions, that spans in the third dimension that shows where those cross on the imaginary plane. I'm sure that that's provided somewhere, and we could look up something like that. We just can't see it on a real axis. So when we say imaginary, it doesn't mean made up. It means unvisualized in our real system. So, it just goes off in that way. Now, I know that, what's his name? The guy did Gaussian. I guess his name is Gauss. I don't know if it's Charles Gauss or whatever. I think Gauss had come up with another term for them, calling, I think, the real numbers direct numbers, and calling the imaginaries lateral numbers. It's kind of a parallel step in another direction, another dimension, if you will, that calls them those. So if we called these, instead of real and imaginary, if we called them direct and lateral, we could do that. Then we'd say there's no direct solution. There are only lateral solutions. You know what's a better thing that we call imaginary numbers? Just call them complex numbers, because all real numbers are complex numbers. All imaginary numbers are complex numbers. And when we get a combination of a real and imaginary, like 3 plus 2i or something like that, that's also a complex number. So sometimes I think they just call the imaginary, if I just had 2i, they'd call it a purely imaginary number. Otherwise, it's still in the complex number plane. So I think a lot of books these days, I think they get off the imaginary numbers part. They just call them complex numbers, and then they call the real component and the imaginary component. So anyway, I hope that answers that there. Why do they do it? I don't know. I'd almost prefer they didn't, because some students devalue them. And when I answered this previous question, what are they used in real life? There's complete value to them. There's appropriate value to them. So I think they devalue them. They're like, why are we learning this then? What does this have to do with? Because they're just as real numbers. So why do they call it? I don't know. Anyway, but I hope I answered it from what I said. Okay, next question. In an equation where you are asked to complete a square, if the a value does not have a number, for example, x squared, does your a value become a 1? Well, yeah, it's a 1. X squared is implied to mean 1x squared. Just like it also means 1x squared plus 0, all divided by 1. Yeah, the implied value in front is a 1. It may be a negative 1 if you're subtracting x squared. It's a negative 1. So I don't know why you're talking about completing the square. This happens in any expression or any equation. However, well, actually it is important. When I state it's good to complete the square, I say make sure that your a value is 1. Okay, in that case, yeah. If it says x squared, that means your a value is 1. So you're good. It needs to be a positive 1 to complete the square, though. So if it's a minus x squared, it's a negative 1. I was just wondering if we're required to turn on our cameras during Zoom for tests. So just keep this in mind just really quick for those who are putting in these questions here. I do want questions to be content-based, related from the last couple weeks. I would have wanted a question like this to have occurred in the curriculum power hour thing. That's not to say you can't ask this question. I am to say I won't give you credit for this question unless you ask this question on top of it, in which case you'll get that credit. I will answer this though. During group test, I encourage for you guys to turn on your cameras in your breakout room during group test. I really, 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 really suggest that you turn on your microphone and that somebody is screen sharing, though. I really recommend that. If you're having no communication, I'm going to knock you out of that group test and you'll get a 0. Sorry. So make sure you're cooperating in your group thing. In individual test, I do ask that you turn on your webcam if you can. Now, you'll get extra credit the same way that you ordinarily would. However, not just for having your face on it. In fact, this sounds rude. I couldn't care less about your face during a test. What I care about is knowing that you're not using something illegitimate. So if I see your face and I see that you're talking to someone or you're talking on the phone, that's a problem. What I'd prefer to see is, well, actually here, this is fine. And here's what a lot of people do, because they want to get the extra credit, I guess. And they want to make it seem like they're not cheating, which is good. I trust that you only have your one phone, but if you show me your phone, if you turn on your webcam, you show me your phone, you show me that you toss it. Let's see, can you see this? You show me that you toss it to the side, and you keep your webcam on the entire time, and I know that you're here, and that you didn't move to go get your phone, or that you didn't turn off your webcam at any point, then I can kind of trust you're not using your phone. And if your face is on the screen, that's fine. Otherwise, I'd prefer that you, and when I say prefer, I mean if you want that extra credit, I'd prefer that otherwise you are having your camera, some people just have their camera right on their phone, and it kind of shows that they're not using it. You know what I mean? And then some people have their camera kind of on like their table, like it shows their hands, it shows their paper. It might even show their phone right next to them. It just shows that they're not using it though, because now I'm watching. I have a watchful eye of it. So are you required to turn on your webcam? I can't require that of you. I'm not allowed to. The only time someone can require you to turn on your camera during a test is if you were like in a sign language class and you needed to actually show someone that that's actually a part of the test, that you're showing the signs, or that if it's like a dance class and you got to show your awesome belly dance or something like that. I don't know what you guys do. But anyway, those are the only times. I can't require it. But if you want extra credit, you're going to have to do that following stuff. All right, how do you do the problems that are like 8i 9 square 5 root squared? I assume that square 5 means square root of 5. So I don't know what the 9's doing there, unless you mean the 9th root. So I'm going to transcode what you wrote here. 8i, you're either saying 8i 9th root of 5 squared, or maybe the 9 wasn't supposed to be there. So it's 8i times the square root of 5 squared. We haven't looked at the former, so I'm not going to dive much into it. I mean, there's not much to it other than the 9th root is also to the 1/9 power, things like that. But we've only been really dealing with square roots when it comes to I, because that's the whole concept. Taking the square root of a negative number is what leads to the I in the first place. So let's talk about a problem like this. And I imagine you're not talking about 9 there unless you're multiplying. I imagine you're not saying that. We haven't really seen that either, but it's no different. Just keep in mind right here, what you have is a product. Okay, I'm going to try and answer this generally first. What you do is this is a product, so you square every portion of the product. You square every portion of it. And what happens when you square the square root of something, the square and the square root cancel, so you're just left with the base. So what I'll do in this scenario is you multiply. These are all multiplying. So when I square this thing, know your exponential property, I would square the 8, I would square the I would square the root 5. Now I'm just going to say the rest out loud because I want to make mention of the, first of all, I want you to try it, I guess, but I also don't want to just do this one problem. When I square the 8, I get 64. When I square the I get I squared. I squared becomes -1. So the I goes away, you're left with a negative result. When I square the square root of 5, I get 5. So now I have -64 times 5, which is -320. So I get -320 answer there. But so the idea is you square every component, and the I that gets squared becomes negative. The square root that gets squared just gives you just the base value. And the 8 that gets squared becomes a 64, or you square that number. So you square each part. I don't know what the 9 had to do with it. I'm not going to make any assumptions of that. So I trust that I did that correctly. All right, where are imaginary numbers used outside the classroom? I'll just go and say that I did where is it used in real life? A few questions above here. It was up here, the small font one. I'm going to go ahead and give you the timestamp to that one so you can kind of see what I answered there, and you can happily answer your own question with that if that's okay. All right, what kind of work should we show on scratch paper for finding growth or decay factor and Y-intercept? Well, it depends on if you're given the equation or the graph. I know I haven't done much with you guys when it comes to given the graph, write the equation. I imagine I could possibly do that because I did give you a worksheet where we did do that once. But if you have, I'm just going to do this generally. If you have y equals ab to the x power, the a value is the y-intercept, and the b value is the growth or decay factor. There is no work to show in that regard. The only way that you might have to show work, like I said, is if you have a graph and you need to come up with it. So, well, you wouldn't have to for the y-intercept. The y-intercept is still the a. That's still the a. And the b, if this is your growth, if that's your graph here, the b comes in the form of, here's when x equals 1, here's when x equals 0. What's the y value there? I'm not going to use a bunch of letters and stuff, but you do this number divided by this number, because you got to find out this number times what gives you this. You do this divided by this to figure it out. When we do, well, not we, but when you guys do systems of exponential functions, equations, and you solve those, I hope your teacher brings into the context enough of why the b value becomes what it is when you're doing the division on one equation on top of another, the reason why we divide and how it connects with your graph here. But you would show some work on those things there. I don't think you're necessarily going to be tested. You're not required, you're not expected to be able to do something here. If it is, it might be from an extra credit question or something. But No work to show. It's there. It's there. The numbers are from the equation. It's like in slope-intercept form. What's the slope? What's the y-intercept? How do you show work? The equation tells you what it is. And that's all. Okay, so thank you for the question, though. All right, let's see. Next question asks, whoa, I just erased someone's question. Next question asks, how do you easily tell if you need to use the quadratic or completing the square? I assume you mean quadratic formula. Basically, what parts of the equation tell you the most about which to use? So I do have a pros and cons sheet. This was from last semester, but if you find my section, I think it was 9.4. Remember, it was like an extra credit one. You can find a pros and cons sheet that actually tells you all of it, but I'll give you the nitty gritty here. Remember that you can use one or the other interchangeably. You always can. There's never an exception, mostly because the quadratic formula is a result of the proof in the quadratic formula is by completing the square. I might have shown you guys the proof last semester, just actually having it already written out. The quadratic formula is a shorthand way of saying, hey guys, we could also plug these things in, but that comes from completing the square. So they can be used interchangeably for any quadratic equation ever. So if you ever just want to use one completely, you can. In which case you'd probably be sticking with quadratic formula. I would not recommend using completing the square in certain kinds of problems. Now you're asking which problems to use one versus the other. When in doubt, use quadratic formula. You've seen me encourage using completing the square anytime completing the square is kind of best used. And when are those times? I would use completing the square. Let me say it out loud instead of write it. I'll show examples. I would say use completing the square if your x squared term has a positive 1 coefficient. It's a 1x squared. And if your linear term is even. Because you got to do the whole dividing by 2 and square it. So you can't complete the square unless you have a 1x squared. And here's where I can here's why I want to write something down. Let's say I have an equation that says something like this. 2x squared plus 4x plus 10 equals 0. And you got to solve the quadratic equation. Whether you use quadratic formula or completing the square, guys, I would recommend you divide everything by 2. So listen, this isn't a 1x squared. So you shouldn't use completing the square. But if you divide everything by 2, then it does become a 1x squared. It becomes x squared plus 2x plus 5 equals 0. I have a 1x squared. I have an even linear coefficient. I'm going to solve by completing the square myself. You want to use quadratic formula, that's fine. But it's these situations that I like using completing the square. Positive 1x squared, even linear coefficient. Now, if this was a 6 instead of a 4, it might look even to begin with, but when you divide it by 2, that 6 becomes a 3. Suddenly, this is not enticing to use completing the square. I know how to do it. I just don't want to deal with the fraction common denominator stuff if I don't have to. So I'm going to use quadratic formula in this problem now, suddenly. Now, you might say, well, it was even before. Shouldn't I use it then? But this wasn't a 1x squared. And I'm not going to get deep into the why it has to be 1x squared, stuff like that. If you look in the book, they kind of show a different way to do it. I know people have tutors and different teachers show the book form. Even Bullock might show that. There's a specific thing I've been showing you, divide it by 2 and square it to complete the square. If you're comfortable in completing the square, I would always use it in the situations where you have the positive 1x squared and even linear coefficient. I think it's less steps than quadratic formula. I think it's less, there's no fraction ever when you're doing that. It's smaller radical that you'd have to simplify, if at all. So I would use completing the square if you know how to use it in those cases. Case like this, or when this is non-1, non-positive 1, I would use quadratic formula. Now, if it's factorable, you can try to do the factoring as well, but when you're comparing one versus the other, I hope that shows it. That's the nitty-gritty of it. If you want to see more, I have a whole pros and cons sheet and a whole video, like a 50-minute video that breaks down every single bullet point of the pros and cons thing. No, I'm sorry, that does not have a video. I'm thinking of a completely different class for a different pros and cons sheet. But look at the pros and cons sheet. If you, I got to attach it somewhere for you, but find the completing the square quadratic formula. You can always use it for either, in either case, interchangeably. But for completing the square, get a 1x squared, get a even linear coefficient. Otherwise, if you don't know how to do it, if you're not comfortable with it, I would just use quadratic formula. All right, next question. If you have an I squared times a negative number, does it equal a negative or a positive? Well, it equals a positive because I squared is negative 1. Negative 1 times a negative number equals a positive number. All right, will we work on more word problems in the future? I don't know if geometry, I assume geometry is going to cover some things. They might be wordy and you got to set something up. Most of the word problems are probably done in algebra. rather than geometry. But if you're talking about just future math stuff, yeah. Oh, absolutely. Of course. For us, past this unit, once we hit geometry stuff, probably not as much. I don't know if we get in surface area volume. I think that's saved for IM3, so not as much there. Probably not as much. I mean, every so often, but they're different kinds of word problems then. They're not the kinds that we're talking about here anymore. So in the geometry, I don't know the answer. Just not as much and not in that same way that you'd be thinking about word problems right now. All right, the next question, what are complex numbers used for? I will say that I answered this already. I'll give you the timestamp for it. It wasn't the best answer. I would always say Google this, but they might go above. Everything we answer for, it's going to go a little bit above your head because they're not used for things that we're going to be talking about right now. But they are, in math, in algebra, they are used to explain things about polynomials. I'll state that. Look up fundamental theorem of algebra as well, and that can help explain something. Basically, there is an importance for them. Don't think that just because they're called well, you said complex, but just because imaginary numbers are called imaginary, don't think they're unimportant. All right, when identifying an imaginary number, what happens when it's followed by a real number? I don't know what you mean when identifying one. Maybe you're talking about when we did the assignment and you have something like a complex number in the form a plus, and you know, we haven't said this very much, but a complex number appears in the form a plus bi, where you have what's called the real component and you have what's called the imaginary component. Now you said when it's followed by a real number. Normally they write the real number first, but what happens, when identifying an imaginary number, what happens when it's followed by a real number? So if you have bi plus a, I don't know what you're asking, but identifying the imaginary portion is this term that has the I multiplied by it, and here's the real one. So what happens if the real number is written after? I don't know. It's written after. I would probably write it first because that's just kind of the standard form of imaginary, of complex numbers. I don't know if that's what you're asking, though, so I couldn't tell you. If you're talking about something like I root 7, because root 7 is a real number, they're multiplying. But what happens when it is? It's a part of it. That's a part of the imaginary number. There's a real number multiplied by I, which makes this an imaginary number. Yeah, I'm sorry. I don't know if I'm answering your question right. I hope I did, and if so, then you can get your kind of points for this part. Okay, sorry about that. All right, on the test, when we get a question that says to complete the equation in a perfect square, I don't know if you mean complete the square, are you going to give us an option to use other methods such as quadratic form? I assume you mean quadratic formula. Would we get docked if we completed it in quadratic formula and still got the right answer? So, okay, yeah. So I think what you're asking is this. On the test, if it told you to solve by completing the square, but you used quadratic formula, I guess you would be docked. Listen, I'm not going to be your only teacher ever, so I'll let you know that when I teach you and when I test you, I will not force one on you, so to speak. If you remember the last test that we did, though, there were parts on completing the square you were still required to know. Because if you remember, that test wasn't all just solving. If you remember, I made a very photomath proof test. I don't think I'm going to really be doing that for this test here. But I was making the test in such a way that still tested your knowledge of completing the square and quadratic formula. So it was still important to know one or the other. But on my tests, when you solve a quadratic equation, you may use any method imaginable. If it's factorable, you can solve by factoring. But I think we're going to try and avoid making them factorable in that way. I might ask for the discriminant, in which case you need to know b squared minus 4ac and stuff as well. But another teacher might ask you to solve using completing the square and quadratic formula, whatever, in which case they might dock you. What they should do is they should give you enough credit to do certain parts like getting the answer and stuff. But here's what I would say. If you run into that situation, let's say they ask you to solve by completing the square. You kind of know how to do it, but you're more comfortable solving using quadratic formula. If you have time on your test, what I would do is this. I would solve it using quadratic formula to know what the answer is. So that when you go to solve by completing the square the way that you're supposed to, that you try solving by completing the square and you know whether you're doing something right or wrong because you know whether you're getting the right answer or not. Does that make sense? So you are solving by completing the square, but you use quadratic formula to double check your own your own work. Making sure that, did I do completing the square right anyway? And maybe if you get it wrong, maybe you don't know how to do it right from there. But yeah, a teacher might dock you in the future. Remember the practice test I gave you said solve by completing the square. I said it doesn't matter because I didn't make that practice test, so I didn't change that. And I used completing the square whenever I thought it was best for me to. So I feel you can do the same thing. So unless I ask something specific of you, not like solve by completing the square, but if I ask something about completing the square, if I ask you about the discriminant or something like that, and you got to use something specific that way. Otherwise, I don't care. Another teacher will and might. I'm sure they will. They want to make sure you know how to do both. I want to make sure you know how to solve it. I'd prefer that you do weigh the pros and cons and you choose, but I'm going to let you do you. Okay? So I hope that answers that. Now, I'd say that was more of a curriculum-based question. I see there's content within, but that doesn't help clarify what those things mean or anything like that. So I don't know. I'll see how much credit I give you. And the last question here is, I was confused on this problem. 5 plus 2i minus 5 minus 2i. I distributed the subtraction with 5 minus 2i, and then I was left with 5 plus 2i minus 5 plus 2i. And if you add the 5s, it's 0. Technically, if you subtract the 5s, it's 0. But if you add the 5 with negative 5, I get it. So would it just be 4i? You distribute the negative. Yeah, that'd be it. Because that was a very specific question, I don't know if you can really get the credit stuff for that, because I want things where I can cover things more for other people. I hope people understood what they meant when they said that they distributed the negative. The answer is 4i. If you want to write it as a real with imaginary, it'd be 0 plus 4i. The real part is 0. The imaginary part's 4i. It's a complex number still. The answer is 4i. That's it. Yep. Okay, guys, that'll be it for this one here. I think I got under an hour. I sure did. So description section down below, show the timestamps for each part. If you missed anything there, I sure hope that helped. And I'll be back with you guys in a few weeks' time, maybe even a month, because what's going to happen is we're going to test this week, so there's no new content here, and then we have a week off. So when we start the next stuff, guys, I'll probably do another video a month from now on Integrated Math 1 and 2 when we're doing this. So thank you for watching. Take care.